In order to prove that every principal ideal domain is a unique factorization domain, we need to do two things. The first is that we need to prove that every non-zero element of a PID factors into irreducibles in some way, that there is some way of getting an element down to a product of irreducibles. And the other thing that we have to do is prove that that factorization into irreducibles is unique up to ordering of the irreducibles and associates. We're not going to do the uniqueness part in this video, but we are going to prove that every non-zero element of a PID does factor into irreducibles in at least one way. So that's what we'll do here. So theorem. Let X be an element of R, a principal ideal domain, and assume X is not equal to 0. Then there exists a unit U in R and a list, possibly empty, P1 up to PM. Note that this is finite, of irreducibles of R, such that X is equal to U times P1 through PM. Let's put one more in there just so it looks a little bit more representative of a product. And that's the theorem statement. So every element that's non-zero factors into some unit times a sequence of irreducibles. The sequence, of course, since we're in a commutative ring, the ordering doesn't matter. And the sequence may be empty if the X that we start with is a unit itself. If X is a unit, then we don't want to multiply by any other stuff. We have a unit and that's that. And the proof is going to have a couple of parts, a couple of cases. So let's assume X is non-zero. Technically, we did that already in the theorem statement, but that's okay. We can write it again. Assume X is non-zero. If X is a unit, then just pick U equal to X and M equal to 0. The number of irreducibles will be 0. And then we have X equals U, and we are done. That's about as easy as this proof is going to get. In that case, we're done because that X is just a product of a unit and no irreducibles. Okay, so now assume X is not a unit. That's the other case. Now, just a little bit of commentary on the proof strategy here. One thing that you might think of doing, if you're used to working with the integers and are familiar with the proof of unique prime factorization for the integers, here's how that proof works, just a brief synopsis. When we're in the positive integers, what we usually do is we observe that any integer, like let's say 378, I'm just making that up, can be factored into some prime times something else. Either 378 is itself prime, which we know that it's not because we see that it's even. If it's not prime, then it factors into a product of two smaller numbers, like 2 times 189. And then we realize we have a prime here, and then this number is smaller, and we surmise that that can also be factored into primes. And the way we approach this is we actually use induction to show existence of a factorization into primes. So the way it works is we say if this number is prime, then we're done. That's the factorization. If it's not prime, then factor it into two smaller numbers and continue with the proof by induction. That is, assume inductively that you've already factored each of these into primes, and then you know that you have a factorization of this into primes because it's just the product of this times this. That's lovely if you have an order and you can use induction. Here, we're in a principal ideal domain. We don't necessarily have induction. And you might think, well, maybe we could retool the proof by saying, well, let's induct on the number of irreducibles that we need or something. Like maybe if X is not a unit, and if it's not irreducible itself, then X factors into a product of two things, neither of which is a unit. And then each of those things perhaps is factorable into a smaller number of irreducibles, so you use induction. But the problem with that is we have no basis right now for assuming that anything here factors into a finite number of irreducibles. That's the thing that we're trying to prove. So for this, we're going to need to use the fact that a PID is a Noetherian domain. So we are going to use the fact that a PID is a Noetherian domain. And when we say Noetherian domain, we mean An ascending chain of ideals must stabilize. That somehow is going to be the key to this proof. I know it's probably not clear right now how, but we're going to try and show in this video why that is such a help. All right, so back to the proof. So the first thing I'm going to do, because this is going to be an iterative process, is I'm going to define x naught to equal x. And I'm just going to comment here if x naught is itself irreducible, then we're pretty much done. Then just let P1 equal x naught, and then we have x equals x naught equals P1. That is a product of irreducibles, and we're done. So in this case, we're done. Okay, and then the only alternative after that is, well, if we're not a unit and we're not irreducible and we're not zero, then x naught must be factorable into two non-units. So otherwise, we can factor x naught into two non-units. And we're going to call those units x naught equals q1 times x1. And at this point, I'm going to claim we can construct the principal ideals of both x naught and x1, and the ideal generated by x naught is a proper subideal, so strictly less than the ideal generated by x1. All right, we're going to prove that before moving on. So here's why that's the case. All right, so first of all, we know that x naught belongs to the ideal generated by x1, since x naught is a multiple of x1. We see that in this equation up here. So that means that the ideal generated by x naught, which is the smallest ideal containing x naught, has to be at least a subset of the ideal generated by x1. To show it's a proper subset, I'm going to claim that x1 does not belong to the ideal generated by x naught, and here's why. If it were an element, if x1 were an element of the ideal generated by x naught, then that would mean that x1 is a multiple of x naught. So I'll just call that x naught times r for some r in the ring. Okay, but then what do we know? That means that x1 is a multiple of x naught is a multiple of x1, and we're going to run into a conflict here pretty quickly, because x naught is equal to q1 times x1, and then x1 is equal to x naught times r, so we get x naught equals x naught times q1 times r, and because the left side is equal to x naught times unity, and we have multiplicative cancellation, and x naught is non-zero, that means that 1 has to equal q1 times r, and that makes q1 a unit, which is a contradiction. Okay, so that shows that x naught, that ideal, is a subset of the ideal generated by x1, but a proper ideal, or a proper subset, because x1 does not belong to the ideal generated by x naught. All right, therefore, x naught is a proper subideal of the ideal generated by x1. So just by way of keeping track of what we're doing and trying to make this as concrete as possible, here's where we are right now. You could think of 378 as kind of a test case for this argument, even though we have a better argument that works for the positive integers. So here, 378 kind of serves as our x naught. And then we're saying, well, 378, if it's not irreducible, which we know it's not, then it factors into two numbers. And I was going to say two smaller numbers, which is true of the positive integers. But in a ring, we don't really have that sense of smallness. We just know that 378 factors into two non-units. And here those were 2 and 189. Okay, so then what we're really saying is let's take 189 and let's construct the ideal generated by that. Okay, so now what we're doing is we've got this is our first ideal in the chain. This is the x naught ideal. And then this generates a larger ideal. It generates a larger ideal because what we have here is a proper divisor of 378. Now again, we don't have a definition of proper divisor for a principal ideal domain, but we can think of a proper divisor, for now at least, as one that multiplies by a non-unit to give this other element here. Okay, so when we have a proper divisor, we get a bigger ideal overall. So back to the argument. All right, so that's where we are right now. Okay, so what's the next step of the proof? And I'm just going to keep track over here of the fact that x naught was equal to q1 times x1. All right, so at this point, you might wonder, well, is x1 irreducible? It could be. If x1 is irreducible, then great. Stop. Okay, and the reason I'm going to say stop is not because that necessarily completes the proof, because I'm still going to have this problem of q1 potentially not being irreducible, but I'm going to address that in just a minute. Really, at this point, all I want to know is that I can find some irreducible inside of x naught, that there is an irreducible factor somewhere in here, and then we will figure out how to rewrite the argument so that x naught is entirely a product of irreducibles. At this point, I'll be happy if I can just find one irreducible anywhere in here. Okay. So if x1 is not irreducible, then x1, since it's not a unit, it factors as a product of two non-units. Two non-units. So let's say x1 equals q2 times x2. And at this point, without reproducing the entire argument, I'm just going to say we have this original ideal generated by x naught. It's a subideal, a proper subideal of that generated by x1. And now this is a proper subideal of the ideal generated by x2. And now we ask, is x2 irreducible? If so, stop, because I will have shown that at least x naught has an irreducible factor. If not, you know what to do. Write x2 as a product of two non-units. x2 equals q3 times x3. And now at this point, I have a longer chain of ideals. X naught, subideal of x1, subideal of x2, subideal of x3. I'm starting to realize that the less than signs and the angle bracket signs look awfully similar to each other. I'm sorry about that. And at this point, I'm just going to step back and talk about the entire process, because I could keep doing this for paragraphs and paragraphs, and it'd make for an awfully long video. But the point is, if at some point we get an irreducible xn, then stop. We've shown that x has an irreducible factor. If not, if we never get an irreducible, we get an infinite, strictly ascending chain of ideals. X naught, x1, x2. We've already got all of these, but we're going to keep going forever. But we know that we can't keep on going forever. This can't happen since R is Noetherian. So what must happen at some point is, at some point we must get an irreducible. That's the only way we escape creating an infinite ascending chain of ideals. So at some point, so some factor xn must be irreducible. And this xn is a factor of the original x. Because that x was written as q1 times x1, and then x1 was written as q2 times x2, and then x2 is written as q3 times x3, and so on. But that irreducible factor lies in there somewhere. So we've managed to do all of this work, a lot of work it looks like. Wow, that is a lot. And what did we prove? We did not prove our theorem. We failed. Okay, but we failed in a very productive way. Okay, so I'm going to call this proof fail. We only showed that x, which we assumed was a non-unit, non-zero, has an irreducible factor. But that's progress. We didn't show it has a factorization into irreducibles, but we showed it has an irreducible factor. In the next video, we're going to use that to complete the proof of this theorem. You might want to think about, by the way, you might want to think about, if you knew this, which we do know this now, could you complete the proof? I think that you might be able to. Think about how you might just rewrite this argument knowing this so that you have a complete proof that there is an irreducible factorization of x. But in the next video, we'll do the proof together.